process? Okay. So last time I talked about elongation due to tension and thermal expansion. And I did one example of a statically indeterminate system using tension compression. I'm going to do another kind that comes up a lot in the problems, and you see it a lot in textbooks. So let me just start with this example. Let's say you have a beam connected to the wall by a pin joint, and then it's connected to the ceiling by a cable at its midpoint and a cable at its end. And we'll say this is, each of these is half a meter, so the total length of the beam is 1 meter. And there's a downward force applied at the end of 5,000 newtons. What are the reactions? Well, we're going to first do the statics problem, see what we have. We'll see that it's statically indeterminate. And then we'll use the geometry of how these things deform to figure out another equation to relate the variables we have. So free body diagram of the beam. We have a reaction at the wall. Call that R. We have the 5,000 Newton force at the end. And then we have an upward tension. I'll call this one TA. And an upward tension at the end, I'll call TB. Newton's second law says R, X and Y plus 0 TA plus 0 TB plus 0 negative 5,000 is equal to zeros. We can tell from this that R doesn't have any X component. And we get a second equation. I'll number that one equation 1, that says Ry plus TA plus TB is equal to 5,000. And then we'll go to the moment equation. I'll do it about the left end point. There's no moment produced by R. TA has a moment arm of 0.5. And is that a positive or a negative moment? Positive, because that would be counterclockwise. Same with TB, but what's the moment arm for TB?
1.
Yep. And then the moment arm for the 5,000 is also 1. And would that be positive or negative? Negative. So we get a second equation that says 0.5 TA plus TB is equal to 5,000. And now we've done everything we can do with statics. So we just count up the equations, count up the variables. We have 2 equations and 3 variables. So this is statically indeterminate, and we're going to need to come up with a relationship between these variables depending on the geometry of the deformation. Okay, well, if we assume that, and this is an approach you're going to always do with this kind of problem where you have cables attached to rigid bodies. Well, in this class, nothing's really rigid, but we're going to assume that these cables are going to deform a lot more than this bar is going to deform, and that's always going to be a strategy with these kind of problems. So how will this system deform? So if you have, let me draw the original system. You have a cable there and a cable there. And after the deformation, this bar, this beam, cannot move away from that pin joint. And so it's going to be a really small displacement, but if I exaggerate it, it's going to look like this, where you have an amount of stretch in cable A. Okay, so this one's cable A, this one's cable B. We'll call that delta A. And then we have a stretch in cable B that we'll call delta B. And because we're going to assume that they're going to deform more than the beam is going to deform, do you see anything that we can say about the relative lengths of those two deltas? Or where would the logic come from?
The one is a linear relationship.
It's a linear relationship, yep. And you can think of these as you can think of these two as similar triangles. Let me use a darker green here. Okay, so if I exaggerate this, I have two similar triangles. This is the same angle. This length is delta A. This is delta B. This is 0.5. And this is 1. Okay, so thinking of these as similar triangles, you know that delta A over 0.5 is going to be equal to delta B over 1. Or delta A is 2 delta B. So now if you think about where those deformations come from, if those two cables are the same materials, you know, if these two cables are the same, the Young's modulus for cable A is equal to the Young's modulus for cable B. And the cross-sectional area for cable A is equal to the cross-sectional area for cable B. We know that delta A is going to be equal to the tension in cable A times the length. That's going to cancel out. That's the length of the cable. Divided by EA. What? Delta A is...
Should be 2 delta A is equal to delta B. Otherwise you got it 4 times as long. Right?
oh, I see. Yes. Thank you. Yes. So we have delta A is equal to 1/2 delta B. Yes, thanks. Right. I have room over here, so I'll do it 0.5. Thanks. And delta B is equal to TB times that same length. Those cables have the same resting length, divided by EA. And now we can use that in this constraint equation, this red star equation. So we'll use these in the red star equation. And we get that TAL over EA is equal to 0.5 TBL over EA. In this case, a lot of stuff cancels. The L's cancel, the E and the A cancel, and you're left with TA is equal to 0.5 TB. And this, we'll use this as our third equation for our system of 3 variables. So for example, we can just plug these in here. So our new system is RY plus, you can write it as 3TA is equal to 5,000. And our second one, if you make that substitution, so we have 0.25. Oh, we want to use TA. Okay, so 0.5 TA, and for TB, we'll substitute in 2 TA. So 2.5 TA is equal to 5,000. So we just got this from substituting in equation 3. And if you solve it, you get RY is equal to negative 1,000. T, have these named differently, TA is equal to 2,000, and TB is equal to 4,000. Okay, so if you have any of these problems where you have multiple cables attached to a beam, you're just always going to draw out those similar triangles and use the lengths of the legs of the triangles to come up with the ratios of those forces. Any questions about that example? They don't have to be, there's nothing that says those cables have to have the same effective area or effective Young's modulus, and those could be given separately. Then you'd still have an equation like this, but E and A just wouldn't cancel out, or those lengths don't even have to be the same. But you can come up with a relationship just by plugging in. Okay, so now let's go to the next type of macroscopic deformation. And that's angle of twist. Okay, so say you have a cylindrical torsion member. And you apply a torque this way to one end and an equal and opposite torque to the other end. Before the deformation, you could imagine, painting, drawing that line on there. After the deformation, you're going to get a new line. That line's going to move like this. That's exaggerated compared to the ones we're going to deal with. But you get a change in the angle of this line from the green to the red because of that torque. And if you measure this angle, call that phi, that's the angle of twist. To calculate that, the integral definition says phi is equal to the integral over the length of the torsion member of the internal torque dx over a g of x times the polar moment of inertia. Where g of x, g, is equal to e over 2 times 1 plus nu. You've seen that combination of things before. Do you recognize where that's from? Yeah, that's the reciprocal of the shear terms in the compliance matrix. So 1 over g is the shear element in the compliance matrix. And so we don't see the stiffness matrix as often, but G is the shear element of the stiffness matrix.
What's that capital L again, sir?
L.
In the integral definition from 0 to L.
Oh, the length of the member. So this whole thing. Before and after are always the same to us. That's the beauty of being able to assume small deformations. We're not going to use this integral form. We're going to use finite forms, just a finite formula. So if you have piecewise constant torsion members, you have either the angle of twist is equal to internal torque times the length over GIP. That's if all these values are constant over the whole length. And if they're piecewise constant, then the angle of twist is equal to the sum over all the individual pieces of the torsion member of TI, LI over GI, IPI. Okay, so let me do an example. So say that you have this bar coming out of the wall. It's 0.6 meters long. And the only external load on it is a 700 Newton meter torque on the right end. And I'll just give you these values. G, let's say, is equal to 80 times 10 to the 9th pascals. And the polar moment of inertia is 1.57 times 10 to the minus 8th meters to the 4th. And we just want to calculate the angle of twist. Well, first we have to know the external loads, then we have to calculate the internal loads. The only loads that are being applied here are torques about the x-axis. So we have a reaction torque, TR, a torque here of 700. The moment equation about the x-axis says TR plus 700 is equal to 0. So that reaction torque is negative 700. And now we can calculate the internal torque. There's only one cut here, so this is valid for all x's between 0 and 0.6. after I do all this, we're just going to get the values you knew we were going to get from the start, probably. But we have a torque this way of 700, an internal torque, fancy T. So the moment equation about x says negative 700 plus T is equal to 0. So the internal torque over the whole thing is just positive 700 Newton meters. So do any of these change over the length of the beam? T, G, or the polar moment of inertia? Any of those vary? No. So we're just going to use that simple constant value formula. So the angle of twist is just equal to the torque times the length over G IP. So that's 700 times 0.6. G was 80 times 10 to the 9th. And the polar moment of inertia was 1.57 times 10 to the minus 8th. And if you do that calculation, you get 0.334 radians. These answers are always going to be in radians. What? Can it vary? Oh, that's a good question. I think I can't imagine how it could vary continuously, but you could have different members fused together, and so it could change at specific points. But yeah, G is just a material property, and so it's hard to imagine how you could get it to vary continuously or anything like that. Any questions about that? Okay, so now let's use that in a statically indeterminate system. With torsion. Okay, so let's say that you have a bar fixed between two supports. And at the center, there's a torque applied. The whole length of the bar is 1/2 meter. Let's say that it has a circular cross-section with a radius of 1 centimeter. And the Young's modulus is 200 times 10 to the 9th. And Poisson's ratio is 0.3, so it's steel. This is Pascal's. And we want to know what are the reactions. So in a problem like this, the geometric requirement that we're going to use to get our extra equation is one that says at the left and the right, you can't get any angular, change in position of those two ends. Those are welded to the wall or whatever, fixed rigidly. So this can deform. You can get some angle of twist between the left end and the middle, or the left end and somewhere before the right wall, but the angle of twist over the whole length has to be equal to 0. Whatever, I mean, this can deform and this can rotate in a way so that at the midpoint, this can be twisted 1 radian or whatever. That's a lot, but you know, it can be twisted some finite amount. But the requirement is that by the time you get back to the other wall, it has to have gone back. Okay, so we're going to require that the total angle of twist is equal to 0. Okay, so the first thing we have to do is the statics. Draw a free body diagram of the whole thing. At the left, there's going to be some torque. I'll call it TL. In the middle, there's the applied torque of 500 Newton meters. And then at the right, there's going to be another applied torque, TR. I'm not trying to figure out any directions on those torques. I'm just going to assume they're positive, and the signs will work out on their own. So the moment equation about the x-axis says TL plus TR plus 500 is equal to 0. So our first equation, I'll write it as TL plus TR is equal to negative 500. That's one equation, 2 variables. So that's statically indeterminate. So now we're going to use that geometric constraint equation that has to do with how the material deforms. Well, what we need is an expression for we need an expression for the total angle of twist of the beam. And in order to do that, we have to do cuts and come up with expressions for the internal torque based on variables we already have. So how many cuts do we have to do here?
2.
2 cuts. Cut 1 is valid for x values between 0 and 0.25. We have the torque over here of TL. And then the internal torque that we're trying to calculate. So the rotational equation about x says TL plus T is equal to 0. Or in other words, the internal torque over that first cut is equal to negative TL. Whatever TL is, the internal torque is the opposite of that. Then the second cut is valid for x's between 0.25 and 0.5. On this cut, we have TL. We also have the 500 Newton meter torque at the center. And then we have our internal torque, fancy T. So the rotational equation says TL plus 500 plus fancy T is equal to 0. So fancy T is equal to negative TL minus 500. So this first expression gives us the internal torque in terms of the variables we've already defined for the first half, and then this expression gives it in terms of the variables we already have for the second half. The total angle of twist is equal to the angle of twist on piece 1 plus the angle of twist on piece 2. So that's equal to the internal torque on piece 1 times the length of piece 1 over GIP plus the internal torque on piece 2 times the length of piece 2 over GIP. And we can substitute in these expressions that we found, because the problem is right now we know that we can set this equal to 0, and we could set it equal to 0 right here. It's not wrong, but that would give us a third equation that introduces 2 more variables, and it doesn't help us. That's the reason that we did these cuts, to express our internal torques in terms of variables that were already in equations. So we have negative TL times 0.25 over GIP plus the quantity negative TL minus 500 times 0.25 over GIP, and that all has to be equal to 0. Well, you can multiply both sides by GIP and cancel some stuff, and you can divide by 0.25 too. So if we simplify this a little bit, we get negative TL minus TL minus 500 is equal to 0. And so our third equation says negative 2 TL is equal to 500. So now we have a system of 3 equations and 3 variables. We can calculate TL. That lets us... Oh, no, we only had 1 equation, didn't we? So now, sorry about that. Change this to, this is equation 2. So this tells us that TL is equal to negative 250 So TR is, it's the same, right? Or are they equal and opposite? Negative 250. Yep.
So is there a proportionality with that? Like if you move that T
Yes.
away?
Yeah, the closer, the one that load is closer to takes more of the load. Yeah.
Like would that be linear, like at 0.25, then we'd expect negative 125, and then 375?
Yeah, and you can see where it comes in. It just comes in with the lengths of those members. The length of each individual cut or each individual piece in the sum. Okay, one other question. So say that the original problem didn't ask for, you weren't asked for the loads at the walls. You were just asked if this was going to break, okay? In order to figure out how likely this thing is to break, you need to calculate the stresses. But you can't calculate the stresses without calculating the external loads, right? Those stresses come from knowing what the internal loads are. You can't calculate the internal loads till you get the external loads. So you'd have to go through this statically indeterminate system process to figure out the external loads, then the internal loads, and then calculate the stresses. So this is all necessary stuff to figure out the stresses, which is usually our main goal. Any questions about that? Okay, well, let's take a 10-minute break, and when we come back, I'll do an example that has tension and torque in it, and we'll just see how superposition of these things works. Anybody have any questions about the examples we did? Okay, so let's say that now we have two fixed supports and a bar in between them. The whole thing is 1 meter long. And let's say 1/4 of the way along the beam, we have a torque applied of 1,000 Newton meters. And a tension of 4,000 newtons. So let's say that Young's modulus is 100 times 10 to the 9 pascals. Poisson's ratio is 0.3. And it's a circular cross-section with a radius of 1 centimeter. And let's say that in addition to this, the temperature is also decreased 50 degrees Celsius. What does that say? Decreased 50 degrees Celsius from the zero load temperature. And the coefficient of thermal expansion is 5.0 times 10 to the minus 6, 1 over degrees Celsius. The first thing we have to do is the statics. this time we have to deal with torques and horizontal forces at the walls. So at the left, I'll call this fancy TL and RL. And then we have the torque of 1,000. The horizontal force of 4,000. And then on the right end, we have a reaction. Right end, we have the reaction torque, I'll call TR, and then the reaction force, I'll call RR. Anybody unclear why that, like why doesn't the temperature go in there?
On the free body diagram?
Yeah.
Because that changes after we...
Yeah, right. So we apply that at the as a constraint afterwards, and the temperature, like the temperature decrease in a way really does show up here. It's just going to affect those values of the reactions. So all that's already included in what we have. So Newton's second law, I'll just do the x component. It says RL plus 4,000 plus RR is equal to 0. So we get this first equation that says RL plus RR is equal to negative 4,000. And then the rotational equation about the x-axis says fancy TL plus 1,000 plus fancy TR is equal to 0. And so our second equation says fancy TL plus fancy TR is equal to negative 1,000. And that's all we can get out of the statics. So we have two equations. Four variables, and so this is statically indeterminate. So we're going to have two requirements, sort of two. The constraint equations are going to come from two requirements. The first one is that the total change in length has to be equal to 0. And we can break that up into total change in length due to internal tension plus a total change in length due to thermal expansion. And then the second requirement says the angle of twist total has to be equal to 0. Okay, so let's do elongation first. In order to do the elongation due to the internal tension, we have to do cuts and calculate those internal loads. How many cuts do we need? 2. Okay, so cut 1 is valid for x's between 0 and 0.25. And actually, maybe let's just calculate the internal loads and not think about elongation versus torsion for now. You know, we'll just calculate them all at once and then go back and use the values we have. So the first cut, we have the left reaction. We have the left torque. And then we have an internal tension and an internal torque. Newton's second law, if we just look at the x components, says RL plus T is equal to 0. So T is equal to negative RL. And then the moment equation about the x-axis says fancy TL plus fancy T is equal to 0. So the internal torque is equal to negative TL. And then cut 2. For x values between 0.25 and 1. So we still have those same 2 loads on the left end. Now we also have a torque of 1,000. And a force to the right of 4,000. And then the internal tension and internal torque. So Newton's second law about the x-axis says RL plus 4,000 plus T equals 0. So T is equal to negative RL minus 4,000. And then the moment equation about x TL plus 1,000 plus fancy T is equal to 0. So fancy T is equal to negative TL minus 1,000. Okay, so now we have all the internal loads. So now let's think about the requirements for elongation. The total elongation due to internal tension is equal to the elongation on that first piece, where T is equal to negative RL, times the length of 0.25, times the Young's modulus. It's not going to cancel out this time. So that's 100 times 10 to the 9. times the area, which is 0.000314. That's for the first piece, and then the second piece, the internal tension is negative RL minus 4,000 times the length of 0.75 divided by the same stuff, 100 times 10 to the 9, and then 0.000314. It's pi times 10 to the minus 4.
Where'd that come from, sir?
The radius was 1 centimeter, so
Oh, okay.
yeah, the area. And then the thermal expansion the elongation due to the temperature change is equal to 5 times 10 to the minus 6. That's the coefficient of expansion. Times the total length. We don't have to do cuts or anything for the thermal expansion. Times the change in temperature. This is a decrease of 50 degrees, so that's negative 50. So you get an elongation of negative 2.5 times 10 to the minus 4. So it shortens, just due to temperature, it would shorten by 1/4 of a millimeter. It doesn't sound like very much, but it's going to have a big effect on these forces. And now we'll put them all together. So the total elongation is equal to negative 0.25 RL over, if you put these all together, you get pi times 10 to the 7th minus 0.75 times RL plus 4,000. I already pulled the negative out. Over pi times 10 to the 7. Minus 2.5 times 10 to the minus 4 is equal to 0. And if you do some fiddling around, you get negative RL minus 3,000 is equal to positive 7853.98. So far, what did we have? A system of 2 equations and 4 variables, I think. So this would be equation 3. And now we'll go to the angle of twist. So the total angle of twist is equal to the angle of twist for part 1 plus the angle of twist for part 2. On piece 1, our internal torque is negative TL. The length is 0.25. I think the GIPs are going to go away, so let's just leave it like this for now. and then plus the angle of twist for the second piece. The internal torque is negative TL minus 1,000 times 0.75 divided by GIP. And those have to add up to 0 because of the fixed constraints at the wall. And so we can multiply both sides by GIP, and those cancel. And you get that negative TL is equal to 750. So your fourth equation is that internal torque at the left end is equal to negative 750. So now that's 4 equations, 4 variables. So you already have TL, fancy TL. RL is negative 10,853. Then you can plug that back into equation 1 to get the reaction at the right. So I believe that's 6,853. So RR is equal to, oh, is it positive? Positive 6,853.98. And then the last thing we need is the torque on the right end. On the left, it's negative 750, so go to equation 2. So negative 250. Any questions about that? One other calculation we could do now using this approach is you could figure out if you did a prescribed, applied some kind of prescribed displacement to the end of a beam. Say you knew that you were going to change the length of the beam 1 millimeter, or you were going to turn the end of the beam, give it an angle of twist of 0.1 radians or something. You could use this same approach to figure out what the loads have to be. Okay, well, let's do the quiz now, but the last macroscopic related thing we have to do is deflection due to bending. And beam deflection due to bending, I don't know if you've ever thought about this, but when you do truss calculations, you always assume that everything's connected by pin joints, right, or ball and socket joints in 3D. But then you look at a bridge or something that, a structure that you're told is a truss, and there's no pins in it. All the members are connected by big riveted gusset plate. And obviously, those act like weld joints. Those can apply couples in addition to forces. So they fundamentally behave differently than pin joints do. This, with pin joints there, it's a statically determinate system. You can use statics to solve for it. Like this, it's really statically indeterminate. And it turns out if you solve it, you get that the couples that those joints apply are small, and basically that's why we do the approximation of treating it like it's pin joints. But once we talk about beam deflections, we could actually do a full calculation of what kind of reaction loads are happening in over a constrained system like this. And believe me, that's going to be great.
Aren't they pin joints anyways, because they're bolted together or riveted together? They'll pivot on those rivets?
They're
Instead of like a weld joint?
Mm-hmm. No, I think they just behave like a weld joint.
Really?
I don't think they pivot at all.
I mean, if you have a truck frame, well, that's supposedly static.
Mm-hmm.
Well, they have to twist.
Uh-huh.
If you weld that sucker solid, then your suspension better do all the work.
Mm-hmm.
I think, isn't it the same type of theory implied with some of these trusses and stuff?
I don't know. It sure doesn't look like it to me. But like if you go and look at the joints, just stand on a bridge and look at it, it's not. You might be right.
I mean, there's got to be some external forces on there, wind.
Uh-huh. Yeah. Well, the members themselves can twist and
Yeah.
stuff. Yep.
Can it be that we treat this as a pin joint, but treat each bolt as a pin joint? That means that the forces on each pin, some of them cancel each other out, and then that's why you don't really see the movement of the pins. So that's why stable. Because it's like you don't see the twist or anything, because let's say the top left is going to prevent is going to be prevented by the bottom right,
Uh-huh.
or vice versa.
Yeah, right. But I mean, I'm just saying that this gusset plate system, if you unhook the bottom,
Mm-hmm.
and then
Well, she's not going to.
and tried to, it's not
She's not going to move.
it's not going to flex like a pin
Right,
joint.
right,
That's all I'm saying. And so that means that that makes it a statically indeterminate system.
Uh-huh.
And to really carefully calculate that, you'd have to use a statically indeterminate approach,